All right, ready for a deep dive. We're going to the edge of the observable universe today.
To the edge.
Yeah. Looking for clues about how the whole universe works.
Ambitious. I like it.
You know me, always aiming high. And what better way to do that than with supernovae?
Supernovae.
Mm-hmm.
One of my favorite topics. There's a new discovery that's making astronomers scratch their heads, you know?
That's what we're diving into today, right? Specifically, type Ia supernovae.
Right, right. Type Ia supernovae. These are a specific type, a kind of exploding star, incredibly bright.
Brighter than our sun, right?
Oh, way brighter.
Yeah.
And what's even more important is that they're pretty uniform in how bright they get.
Like, what's a good analogy? Like light bulbs?
Light bulbs.
Yeah.
Yeah.
Think of them like light bulbs, all the same wattage.
Yeah, same wattage, same brightness, no matter where they are in the universe.
Okay, so we've got our cosmic light bulbs. Got it. But why should anyone care about them?
Well, because they're like the universe's ultimate measuring sticks.
Measuring sticks.
Yeah. You see, by observing a type Ia supernova and seeing how bright it appears, we can calculate how far away it is.
So kind of like, I don't know, judging the distance to a car based on how bright the headlights look?
Yeah, exactly like that. Dimmer means farther away.
Right.
So by mapping out these supernovae, we can trace the expansion of the universe.
So not only are we talking about exploding stars, but we're also talking about the expansion of the universe, dark energy, all that stuff.
Exactly.
This is big.
And that's why this new discovery is so exciting.
Yeah.
The James Webb Space Telescope, JWST.
Oh, yeah, our super-powered space eye.
Exactly. It's spotted a type Ia supernova farther away than most we've ever studied before.
Wow.
It's called SN 2023X.
SN 2023? All right, I gotta ask. How did they even find this thing? It must be incredibly faint at that distance.
Oh, incredibly faint, you're telling me.
Yeah.
It's a huge challenge to find supernovae this far out. I mean, the light from these events, it's traveled for billions of years to reach us.
Billions of years. Wow.
Imagine a whisper traveling across a crowded room. That's how faint these signals are.
So how did they pick it out from all that noise?
Well, it all started with the Cosmos Web Survey.
The Cosmos Web Survey. Yeah.
Basically, a huge project using JWST to map a large patch of the sky.
Right.
But here's the thing. It turns out that SN 2023X, it was actually captured in an earlier image.
In an earlier image.
Yeah, totally by chance, from a different survey called Panoramic.
What a lucky break. So they had two images then, years apart.
Exactly. Two images years apart gave astronomers the clue they needed.
Like finding a needle in a cosmic haystack.
Right. They saw something in the newer image that wasn't in the older one, and that sparked a whole investigation.
Okay, so they had their suspicions. What did they do next?
They launched a dedicated observation campaign using some of JWST's most sensitive instruments, like the NIR spec.
NR spec, okay.
Acts like a cosmic prism.
A prism?
Yeah, splitting the light into its component colors.
Hold on, why is that important? Splitting light.
Well, think of it like a fingerprint.
A fingerprint, okay.
Every element in the universe emits and absorbs light at specific wavelengths. So by looking at the spectrum, the fingerprint of light, we can figure out what it's made of and what kind of event produced it.
So they're analyzing the light from this distant explosion to figure out what it actually is. It's like cosmic forensics.
You got it. Now get this. SN 2023X has a redshift of 2.15.
2.15, okay.
Okay, imagine you throw a ball, and as it travels, it starts stretching. The further it goes, the more stretched out it gets.
Okay, I'm visualizing.
That's kind of what redshift is. Light from distant objects gets stretched by the expansion of the universe.
So the further away it is, the longer the light's been traveling, the higher the redshift.
Exactly. A redshift of 2.15 means we're seeing this supernova as it existed over 10 billion years ago.
10 billion years ago. This is blowing my mind.
This kind of detailed study was impossible before JWST. We're talking at a whole new era of observing the universe.
Wow, a new era. Okay, so they had this distant object, they split its light, analyzed the fingerprint, but how did they know for sure it was a type Ia supernova? There are a lot of things that go boom in space.
Lots of things, yeah. It wasn't easy. There was some initial uncertainty because they couldn't get a precise redshift measurement from the host galaxy itself.
The host galaxy.
Yeah, the galaxy where the supernova occurred.
Yeah.
So they used this clever technique called photometry.
Photometry, okay.
Imagine looking at a light bulb through different colored filters.
Okay.
That's kind of what they did. They analyzed the brightness of the supernova in different colors to estimate its redshift.
Okay, clever. And what was the redshift?
Turned out to be about 2.25.
2.25. Okay, so that's pretty close to the redshift they got from the light itself. Sounds like they're on the right track.
Right. But how do they go from this blurry dot of light
Yeah.
to saying, yep, that's definitely a Type Ia supernova? It's a big leap.
Yeah, how do they know for sure?
Well, that's where the serious analysis comes in.
All right, lay it on me.
They used a sophisticated tool called NGSF, stands for Next Generation Superfit. Basically, it's like a giant cosmic database.
A cosmic database of explosions.
Kind of. They feed the observed spectrum of the supernova into this program, and it compares it to a library of spectra from known supernova types.
Okay, so they're seeing if the fingerprint of this mysterious explosion matches any known fingerprints in their database.
Exactly.
And did it match?
It did. SN 2023 kayaks closely matched a normal Type Ia supernova. Remember how we said Type Ia supernovae are like standardized light bulbs?
Yeah.
Well, even across these vast cosmic distances, scientists can identify the specific signatures of these explosions. It's amazing how consistent these patterns are across the universe.
Wow, that's incredible. So they confirmed it is a Type Ia, but remember, we talked about using these supernovae as cosmic measuring sticks. How does that actually work? What do they do with this information?
Well, once they confirm the type, the next step is to precisely measure the distance to SN 2023X. And to do that, they use a powerful tool called the Bay-SN model.
Bay-SN model. Got it.
Imagine you're analyzing the fading glow of a firework
Okay.
to understand its explosive power. That's kind of what they're doing here.
So they're studying how the supernova's light changes over time to figure out how far away it is.
Yes. And this model is incredibly sophisticated. It takes into account all sorts of factors. Things like dust blocking some of the light, the specific way its brightness changes over time, even subtle variations in the intrinsic brightness of different Type Ia supernovae.
Right, so they're not all exactly the same brightness.
Exactly. It's like accounting for the type of firework, the weather conditions, even how far you're standing from the display.
Okay, I see the analogy. So they plug all this data into this Bay-SN model. And what comes out the other end?
A number, of course.
Of course, a number, but what kind of number?
They measured something called the luminosity distance to SN 2023 Eccus.
Luminosity distance. Okay, I'm going to need you to break that down for me. What is luminosity distance?
It's a bit technical, but basically it's a measure of how bright the supernova actually is, regardless of how far away it is or how much its light has been dimmed by cosmic dust.
Okay, so we've got this luminosity distance. What's so special about it? What does it tell us?
Well, the big reveal is that this measurement for SN 2023X is incredibly consistent with what our current understanding of the universe predicts.
Okay, this is good news, right?
Remember our friend, dark energy. Yeah, the mysterious force pushing the universe apart.
Right. So we have this model of the universe called CDM, which includes dark energy, and it describes how the universe has expanded over time. And the luminosity distance they measured for SN 2023 fits beautifully with what CDM predicts.
So basically, this distant supernova is behaving just as we'd expect it to. Based on our current understanding of the universe, it's a win for our current model.
That's one way to put it, but it's not as simple as it seems.
Oh, there's a twist coming, isn't there?
Yeah.
I should have known it wouldn't be that easy.
You know it. Remember that other distant supernova we talked about? SN 2023 ADSI. The very first one confirmed at a redshift greater than 2. Yeah, what about it?
Well, it turns out it's not behaving nearly as nicely. Yeah, SN 2023 ADSI. It's, well, it's throwing a bit of a cosmic wrench into things.
Okay, so what's the deal with this one? Is it just farther away, different redshift, maybe?
It's more than just the distance. While SN 2023X has that classic blue color we expect from a Type Ia, SN 2023 ADSI was unusually red.
Red.
Yeah, and its distance measurement was, well, a bit off from what CDM, our standard model, predicted. It's like, imagine we found two seemingly identical light bulbs, right?
Okay, I'm following. 2 light bulbs.
But one is dimmer than it should be, and it's glowing an odd color.
Yeah.
Makes you wonder if it's even the same type of bulb, you know?
Right, right. So we have one supernova that fits our model perfectly and another that's acting a little, well, off. So is SN 2023 ADSI just a fluke, a cosmic oddball, or is there something more going on?
That's the million-dollar question. And with only 2 data points at these extreme distances, it's impossible to say for sure. We need more data, more supernovae to study. That's where the real power of JWST comes in. It's like we've gone from using a magnifying glass to a high-powered telescope.
So are we talking about a whole new era of supernova hunting then?
Absolutely, we're not just finding these distant supernovae, we're studying them in unprecedented detail. We're analyzing their light curves, comparing their spectra to those we've seen closer to home. It's like we're doing cosmic archaeology,
Mhm.
piecing together the history of the universe from these ancient explosions.
Wow, cosmic archaeology. I like that. Okay, but going back to this weirdness with SN 2023 ADSI, what could explain those differences? The red color, the off-kilter distance, any theories out there?
Oh, of course, there are a few possibilities. Dust, for example.
Yeah.
You know how a sunset looks redder because the sunlight is passing through more atmosphere?
Yeah.
Well, it could be that the light from SN 2023 ADSI passed through a lot of dust on its way to us, making it appear redder and dimmer than it actually is.
Okay, that makes sense. What else?
It could also be that the way type Ia supernovae explode is a bit more, well, complex than we thought. Maybe there are subtle variations in the explosion mechanism, depending on the environment the star is in. You see, the universe was a very different place 10 billion years ago. Galaxies were younger, more compact, and had different chemical compositions. Could these factors play a role?
So maybe the standard in standard candle isn't as standard as we thought.
It's certainly a possibility. Or, and this is where it gets really exciting, maybe we're seeing hints of some new physics at play. Could there be something about the nature of dark energy that we don't fully understand? Something that changes how these supernovae behave at these extreme distances?
Whoa, okay, now that's getting into mind-blowing territory. But how do we go from these intriguing possibilities to actual answers?
More data. We need to build a statistically significant sample of these distant supernovae. Think of it like trying to understand the average height of people,
Yeah,
right?
okay, yeah.
You wouldn't base your conclusions on just two individuals, would you? You need a larger sample size to get a reliable average.
Right, right. Otherwise, you might end up with misleading results.
So JWST, our cosmic data collector, is going to be busy for a while.
Oh, absolutely. This is just the beginning. We're expecting JWST to find many more distant supernovae in the coming years.
That's pretty exciting. But let's be real, if these supernovae are starting to show variations, does that mean our whole plan to use them as precise cosmological probes is, like, out the window? Are we back to square one?
Not necessarily. It just means we need to be smarter, more sophisticated in how we analyze the data. We need to take into account these potential variations, these evolutionary trends. Think of it like recalibrating our cosmic measuring sticks.
I see, so we're not throwing out the tools, just refining them. Exactly. And remember, finding these variations isn't a setback. It's an opportunity. It's pushing us to think harder, to question our assumptions, and ultimately to understand the universe at a deeper level.
I love that perspective. Okay, so we've got this amazing new discovery, SN 2023X, that seems to fit our current model of the universe perfectly. But then we've got this other one, SN 2023 EDS, that's throwing us a curveball with its weird color and unexpected distance. And JWST is out there finding more and more of these distant supernovae, giving us more data to unravel this cosmic puzzle.
You got it. It's an exciting time to be studying the universe. And with every new discovery, we're getting closer to understanding, well, the fundamental nature of reality itself.
And who knows, maybe these variations in type A supernovae will ultimately lead us to a deeper understanding of dark energy itself. Perhaps they'll provide clues about its nature or how it's changed over cosmic time.
It's certainly a possibility.
Yeah.
Wouldn't that be incredible?
Absolutely mind-blowing. So, listeners, we've taken you on a deep dive into the world of distant supernovae, explored the incredible capabilities of the James Webb Space Telescope, and grappled with the mysteries these discoveries present.
We've seen how these cosmic explosions are helping us refine our understanding of the universe, pushing us to question our assumptions and develop new tools to probe the deepest secrets of the cosmos.
But our journey doesn't end here. So where do we go from here? What's the next chapter in this cosmic detective story? So where do we go from here? What's next in this cosmic detective story?
Well, we've talked a lot about these supernovae, as individual events.
Right.
But they don't just happen in isolation.
Right.
Yeah.
Good point. So what are we missing?
They explode within galaxies, and those galaxies have their own stories to tell.
Okay, so we need to zoom out. Look at the bigger picture. What can these host galaxies tell us about the supernovae themselves?
It's all about context. By studying the types of galaxies these supernovae are found in, their ages, their chemical compositions, we can start to understand how the environment might influence the properties of the supernovae.
So it's kind of like understanding a person by looking at their family history and the community they grew up in.
Exactly. So it could be that certain types of galaxies are more likely to host supernovae that, well, deviate from the norm. Or maybe the chemical makeup of a galaxy affects the way these supernovae explode.
That makes sense. It's like, I don't know, how a plant might grow differently depending on the soil it's planted in. So, by studying the host galaxies, we might find clues that explain those weird discrepancies, like we see in some type Ia supernovae, like SN 2023 ODSI.
Precisely.
Hmm.
And JWST is, well, it's perfect for this kind of research. Not only can it detect these distant supernovae, but it can also study their host galaxies in incredible detail, allowing us to connect the dots
Yeah.
in a way that was never possible before.
It's amazing to think that we can study galaxies that existed billions of years ago. Just incredible.
It is remarkable. And as we continue to gather more data from both the supernovae and their host galaxies, we'll start to see patterns emerge, trends that will help us refine our models
Yeah.
and gain a deeper understanding of how the universe works.
It's like we're putting together a giant cosmic jigsaw puzzle. Each new discovery is another piece that helps us see the bigger picture. But I can't help but wonder, what if we find more supernovae like SN 2023 ADSI? What if these variations become more common as we probe deeper into the universe?
That's a fascinating question. If we find that Type Ia supernovae are indeed evolving with redshift, that their properties are changing over cosmic time, well, would certainly challenge our current understanding of cosmology.
So, what would that mean for our models of the universe? Would we have to throw everything out, everything we thought we knew?
But not necessarily. It would mean revising our models, refining our understanding of how these supernovae work and how we use them to measure distances. Remember, science is all about adaptation. New discoveries often force us to rethink our assumptions and come up with new explanations.
So, even if these variations throw a wrench into our current models, it's not a failure. It's an opportunity to learn something new and refine our understanding of the universe.
Exactly. It's like we're on a grand adventure exploring uncharted territory. And who knows what amazing discoveries await us as we venture deeper into the cosmos.
Well said. So, listeners, as we wrap up this deep dive into the world of distant supernovae, we leave you with a sense of wonder and a thirst for more knowledge. We have explored the incredible power of the James Webb Space Telescope, the meticulous work of astronomers piecing together clues from the universe's distant past, and the tantalizing mysteries that these discoveries present.
We've learned that even the most seemingly simple concepts, like a standard candle, can hold hidden complexities, pushing us to question our assumptions and refine our understanding of the universe. As we continue to explore the cosmos with ever-increasing precision, we're sure to encounter more surprises, more challenges, and more opportunities to expand our knowledge of this vast and enigmatic universe we call home.
And who knows what revolutionary discoveries await us on the horizon? Perhaps these variations in Type Ia supernovae will lead us to a deeper understanding of dark energy, or maybe they'll unveil entirely new phenomena that we haven't even imagined yet. The universe is full of surprises, and that's what makes exploring it so exhilarating. Until next time, keep looking up, keep questioning, and keep your sense of wonder alive.
And remember, there's always more to explore.